Hello, everybody. Hilary Ransom would be here to set off this seminar today because it's one of the impact case studies which Hilary has shortlisted for our imminent REF submission. To put that into context for you, if you are on a REF panel, you get to read something like 1,000 papers and score them, and you read them until your eyes bleed. But then finally you get onto the impact case studies, and these are actually quite fun because they tell a story and they show how a piece of research, in keeping with the mission statement of this organisation, which you'll have seen next to the left, how a piece of research then goes on to do some good in society. So let me hand over to Andy to tell you about their particular impact case.
Thank you very much. Hi everybody. I'm going to talk today about tiny targets, which I'm sure you're all familiar with, and go through the work that we've been doing on this tool for TETSI control from an initial research project to now being a large-scale vector control operation. So just to give a quick little bit of historical background, it was back towards the end of the 19th century that David Bruce in South Africa, he was sent to investigate an outbreak of cattle disease, and ultimately he discovered that the disease was caused by trypanosomes and that these were being vectored by tsetse fly. And then in 1902, Joseph Dutton, who's actually from Bebington, so a bit of a link between Liverpool and sleeping sickness from a long time ago, he discovered in Gambia Trypanosoma gambiense as being the causal agent of a sleeping sickness outbreak in that country. And then in Uganda in the early 1900s, there was a huge epidemic of sleeping sickness in the Busoga region, which is estimated to have killed almost a third of the population there, around 300,000 people. And then Aldo Castellani and again David Bruce identified that it was the trypanosomes that were causing this disease, and again they were being vectored by tsetse flies. So I've mentioned animal trypanosomiasis and human animal trypanosomiasis. So yeah, there are two different kinds. Both are transmitted by tsetse fly. So there's the human sleeping sickness and the animal version, which affects cattle and livestock and is called Nagana. And this will be my final slide to talk about animal trips. It's a huge problem in Africa. Affects virtually all species of livestock, over 35 million cases a year, so it's a huge economic impact. About 1 million cattle killed every year, and it's estimated to cost about $4 billion in lost productivity every year. So it leads to less milk and meat production, lower reproductive capacity, less draft power, animals are more susceptible to other disease, and increased mortality. And then for the human side of the disease, well, it's really a tale of two diseases, in fact. So we have two forms. We have the Gambiense form and the Rhizesiense form. Gambiense form is chronic in humans. It's found in the western central part of Africa to the west of this black line. It causes about 90% of all HAT cases in the world, and humans are the most affected by the disease, although there is some animal reservoirs as well. And then the Rhodesian form of the disease, which is found in East and Southern Africa, it's an acute infection in humans. It only accounts for about 10% of all diseases, and here it's mainly animals that are the reservoirs, and then humans as sort of secondary victim, if you like. And then what can we say about both? What are the common things for both diseases? Well, there's no vaccine. There are no prophylactic drugs. Until very recently, treatment has been with very toxic drugs and very difficult to administer drugs, but there is changes in that domain now as well. Ultimately, it's fatal for humans if it's not treated, and it's spread by tsetse flies. and tsetse flies, which I'm sure you're all familiar with, infest a huge area of sub-Saharan Africa. The tsetse belt covers over 11 million square kilometers, stretching all the way from the west across to the east of the continent. And there are two groups of species which are vectors for sleeping sickness. So the riverine species are the important vectors of the Gambian form of the disease. So these are the Palpalis group, and they're found in West and Central Africa. And then the savanna species are the vectors of the Rhodesian form of the disease, and they're found much more widespread actually, but you can see they're in the east and central and the western area. So by the 1960s, things were going well for sleeping sickness control. There was a huge effort for screening and treatment of affected people, and there was a steady decline in the number of reported cases across Africa. So by the 1960s and early 1970s, we were down to less than 10,000 cases per year, which is great. But unfortunately, changes in political stability in countries with the end of colonial era, also people taking their eye off the ball because there had been such a decline in cases and no longer thinking of it being such a problem. This then led to an increase in cases again towards the end of the 70s, through the 80s and 90s, and again we were having large-scale outbreaks in the 1990s. So then in 2012, a lot of international attention on sleeping sickness, and there was the London Declaration on NTDs, which was a commitment to control or eliminate at least 10 NTDs by the end of 2020, one of them being sleeping sickness. And then the WHO also set out their roadmap for eliminating the Gambian form of HAT. And their definition of elimination of Gambian HAT as a public health problem by 2020 meant less than one case per 10,000 people in endemic foci. And for this to be in more than 90% of endemic foci, and less than 2,000 cases worldwide. And then eventually to stop transmission by 2030. And one of the important things in the WHO roadmap is that vector control was included for the first time. And this is a picture of the WHO steering committee, which includes our very own Steve Torr flying the flag for vector control, so that the strategy no longer just relies on screen and treat. So if we're thinking about vector control, what are some of the advantages for tsetse flies, which lead to them being able to be controlled by vector control? Well, they have a very low reproductive rate, one offspring per cycle, unlike mosquitoes, where you can get hundreds of mosquitoes from a single cycle. Both males and females are dependent on blood, so they have to be mobile and seek out a host every few days to get a new blood meal for energy. And there's also been a lot of work on host-seeking behavior to understand some of the cues which lead tsetse flies to hosts in order to obtain that blood meal. So understanding those odor cues and visual cues would help with the development of vector control tools. And this biology means that if we can impose a relatively small mortality rate on tsetse flies, say 4% of the population per day, then in theory we could interrupt the transmission of trypanosomes. So it really does give hope for using vector control for disease control. And then in terms of vector control, there are many options, but for Gambian HAT, very few of them are used. A number of different techniques have been used for Rhodesian HAT, so ground spraying, aerial spraying, odor baits, and insecticidal cattle. But these are not necessarily conducive to controlling the riverine vectors of Gambian HAT. So ground spraying is expensive, it's logistically difficult, it requires a lot of manpower, people going out, spraying in the field, targeting breeding sites to kill the flies. Aerial spraying, not surprisingly, is extremely expensive. Technically, it's also complex. You know, you're using 4 aircraft per night to fly across infested areas and spray insecticide. So they will fly for 100 kilometers, then they will turn, they'll fly another 100 kilometers back in the same direction. So it's expensive, technically complex. Odor baits have been developed for savanna species. These are also relatively expensive. They're large, so they're not very logistically practical for the riverine flies, which are you know, in the forested area along river courses. And then insecticide-treated cattle. This represents the cheapest option for vector control. But unfortunately, in the areas where Gambian hat is endemic, the density of cattle is low. So it's not a feasible option. And then this just shows quickly the different costs attributed to each of those vector control methods per kilometer square. So aerial spraying is up to $535 per kilometer square, whereas cattle spraying is between $50 and $120 per kilometer square. So all of these methods have been developed primarily for savanna species of tsetse fly, but how can we go about controlling the riverine tsetse, which transmit Gambian sleeping sickness? So this question led to the start of a 4-year project by Mike Lahan here at the school and NRI in Greenwich and international partners to look at how riverine tsetse identify a host to feed on. So they started off by looking at traps and targets which have been developed in the 70s and 80s. This is a trap that's typically used for control of flies in where we have riverine populations, but you can tell by the size of it, it's huge. It's not very easy to put that across large areas, and it's extremely expensive, so it's never really been done in a systematic way. And then we have a target with an odor trap, and then one of the large targets used for savanna species. So the group analyzed riverine tsetse responses to different shapes, different colors, host odors, and different sizes. So first of all, starting with different shapes, we looked at whether tsetse are attracted to oblongs or squares, and whether vertical oblongs or horizontal oblongs are attractive. And this work was done in Burkina Faso and DRC, so with Glossina fuscipes in DRC and Glossina palpalis in Burkina Faso. And what they found was that in Burkina Faso, palpalis was attracted to the vertical oblongs more than the horizontal, but in DRC, it was the opposite that was true. It was the horizontal rather than the vertical oblongs that were the most attractive. But interestingly, for both species, they found that a square target of relatively similar surface area was equally attractive to the rectangles. So basically, the take-home from this was that shape-wise, a square is going to work well for palpalis species and also for fuscipes species. And then in terms of color, there was a lot of work done looking at different colors in the 70s and 80s for the savanna species. And Jenny Lind and others looked at this for the riverine species as well, looking at different colors, blue, black, white, green, yellows. And what they found was that, again, it's blue that's the most attractive color, but not just any old blue. It's got to be this phthalogen blue, which, again, is the one that was most attractive for savanna species and is what is used for traps traditionally. So we're now at a square, and it's got to be blue. And then also thinking about odors, because those large savanna targets have an odor bait with them that's based on the odors from ox. And that increases catches of morsitans and polydipes, savanna species, 8 to 10 times when it's added to a target. But doing the same work with riverine species, we don't see this similar level of increase. The maximum increase in catch size for riverine species to ox odor is only 2 times compared to an unbaited trap. And then they also looked at lizards, a more natural host for riverine species, and again compared the catches on targets baited with lizard odor compared to unbaited targets. There was an increase 1.5 times, but nothing particularly strong, unlike the work that was done on the savanna species. So it tends to suggest that for riverine species, adding an odor bait to a target isn't going to be particularly beneficial. And then finally, they also started to look at the size and whether different size targets get different size of catches. Not surprisingly, they do. So a classic 1 meter by 1 meter target is getting 14 tsetse fly, and then a small target, 25 centimeters by 25 centimeters, was getting 6. So you think, okay, well, the smaller target isn't that interesting because it's catching less. But then if you consider it as the number of tsetse per square meter, then that large target is only killing 14 tsetse per square meter, whereas the small one is getting the equivalent of 96. So there's far more bang for your buck using a small target compared to using a large target. So cost effectiveness is much more interesting with these small targets. So you're getting a 7 times greater increase in killing compared to the large target. And then they also found that some flies do land on the target, but others will come to it, they're attracted to the blue, but they'll fly around and then fly away. So how do we kill these ones as well? And this is done with the addition of a flanking net on one side of the target. So it's the same size, 25 centimeters by 25 centimeters, made of mesh impregnated with insecticide. And this time the flies come, they try to fly around the blue target, but they collide with the mesh and take up insecticide and are killed. And they can't see the mesh target, so that's how they collide with it. And so the tiny target was born. And it was found that this was twice as effective for killing flies compared to the traditional traps, which were sometimes used for control. It's also 10 times cheaper than trying to do control with traps. Because the insecticide is impregnated in the fabric in the production phase, it lasts for over 6 months. Previously, when they were using traps, they were just spraying the trap, so it wasn't a long-lasting effect. And of course, because of the size of them, they're far easier to deploy than a large trap, and much more practical for deploying over a large distance or a large area compared to deploying traps. So this then led on to the question of, well, will they actually be useful? Will they have an impact in the field? And this led to trials on islands in Lake Victoria. So we had one island where there were no targets, and one island with tiny targets. And trapping was done on both to see what the population of flies was like. And you can see that in terms of mean daily catch, it's relatively similar in the first few months before targets have been deployed. But then once targets have been deployed from the grey area onwards, there is an immediate decline in the number of flies on the island with targets, and then this persists throughout the experiment. And so we're getting a control of over 99% reduction in fly numbers in this work. And obviously this is an isolated population because it's on an island, but it shows that deploying targets at a density of 10 per kilometer can eliminate populations. But that's just a small island with an isolated population. What about the practicalities in the field? So further trials were done in northwest Uganda, and then in 2014, we started the deployment of tiny targets at a large scale in the West Nile region, deploying them along riverbanks, as shown by the team here. And this is done twice per year, because as I said, the insecticide is effective for 6 months, so we need to do it 2 times to ensure coverage for the whole 12-month period. And so this is really the scale of tiny targets in Uganda. So in 2014, we scaled up to an area of 2,500 square kilometers across 5 districts, which is shown in red here. And that was under our first project targeting Tsetse. And then in 2017, with additional funding under our Trapano project, we scaled up even further, added another 2,500 square kilometers to take us to 5,000 square kilometers across 7 districts. And then since the end of 2019, we've scaled back slightly to 4,000 square kilometers. And to give you an idea, last year in the 2 deployments, it was about 42,000 tiny targets that were deployed along the riverways here. And those are deployed by people on foot. It's a huge amount of effort for the teams, and it is by and large managed by the National Control Programme in Uganda, working through district entomologists who are in each of these districts. And then what's the impact that we've observed of those tiny targets with this population of Tsetse in West Nile? Well, here we can see the catches from sentinel trap sites. So the green bars are trap sites which are outside of the intervention area, so there's no control going on, and the Tsetse population is just continuing as it would. And then the blue bars represent the catches from sentinel sites which are inside the intervention area across those 7 districts. So we can see that there has been a huge reduction in the catch index in the intervention area, and that has now been sustained for a 4-year period. The light grey is the targeting Tsetse project, and then the dark grey is when the Trapano project started in 2016, or 2017 rather. So we've got a sustained reduction of 80 to 90% in the Tsetse population in the intervention area across this time. And Uganda last year only had 2 cases of sleeping sickness, of Gambian sleeping sickness, I should say. And in 2020, they will submit their dossier to WHO for elimination. And then also just to quickly touch on another particular situation for Uganda. We wrote our proposals thinking that we were just working in this fixed area, and then in 2016 there was insecurity and violence in South Sudan, which led to a huge influx of refugees from South Sudan into Uganda, almost 800,000 people coming from an endemic country to a country with a huge amount of control going on and very low case numbers. So with this situation, we added additional vector control around the areas where refugees were settling, expanded Tsetse control operations for an additional 1,000 square kilometers, and there was also intensified screening in the refugee population as well. So it's just to say that tiny targets can also be used in a crisis situation. And when you have a national partner, as we have in Uganda, they're able to react quickly and increase coverage by what was 20% compared to what they were doing previously. So we went from 5,000 to 6,000 square kilometers with the refugee crisis. So that's Uganda. And then with our other partners, we're working in other countries, of course. So one of them is Chad, and our colleague Iñaki Terrados has been quite involved in the Chad intervention. So here it's the Mando focus, which is in southern Chad. Slightly different to Uganda because there's a lot of swamps as well as rivers. So here the tiny targets are deployed along the river and also around the swamps. And again, of course, we have a pre-intervention survey to establish our Tsetse densities before intervention starts, and then we go back to check what the impact has been. So this is the impact of tiny targets on the tsetse population in Chad. So you can see that there is a huge decline. And also, you probably think that it looks like we only went back to check 3 times. But that's not the case. We actually went back on all of these occasions to trap at fixed sentinel sites. But for most of those rounds of trapping, we caught absolutely no flies. The intervention is having a huge impact on the tsetse fly population in this area. And then here, the graph on the left shows the number of hat cases in the Mandel focus, and also the number of people that have been screened. So we can see that before tiny targets were introduced, we were getting between 120 and 140 cases. Tiny targets came in 2014, and we can see that there is a reduction in cases, down to about 45 in 2014, and then down to 20 in 2015. And this decline has continued since then, and screening has maintained at the same kind of level. And then also in the Trapano project, we have added a second focus here in Chad, in the Maro area, which again is also in southern Chad. And then here on the right, we just show the case data for the country as a whole. So you can see the number of cases has dramatically declined, gone from having more than 100 cases a year to less than 10 cases a year. And epidemiological models suggest that more than 70% of this decline is in fact due to vector control, and we wouldn't have seen it if we had just continued with screening and treatment of populations. Also part of the project is Ivory Coast. Here they are working in 2 foci, Bonon and Sinfra. These are relatively small areas, but have very high population densities. And the use of tiny targets here has been really effective and seen over 90% reduction in tsetse numbers over the course of the project. Sorry, the graph here shows the cases, the label's missing. And so you can see from the graph as well that the number of cases in Ivory Coast is also decreasing and is extremely low now. In the 2016 to 2018 period, they only had 5 new cases. And they will also submit an elimination dossier to WHO this year. And then moving on to Guinea. So here, tiny targets are used in 3 different foci. So in Boffa, Dubreka, and Foricaria. Very different to Uganda. Here we're in a mangrove system, dealing with tides as well. And just to show a little bit about the impact of tiny targets. So back in the beginning, they first started working just in Boffa. And Boffa is split into 2 sides, Boffa West and Boffa East, which are separated by the Rio Congo River. So for 2012 to 2013, in Boffa West, there were only medical activities, so screening and treatment for GHAT. And in Boffa East, there was the medical activities, but they also introduced tiny target deployment. And what they saw was that in Boffa West, during this period, there was actually an increase in the prevalence of the disease and an incidence of new infection of 1.09%. Whereas in Boffa East, the target deployment led to a population reduction of 80% amongst the Glossina. And they also had a disease prevalence falling from 0.3% to 0.1%, and an incidence of new infection of 0.07%. So 2 areas next to each other, but very different stories in the 2012-2013 period. And then similar to reacting to a crisis like in Uganda with the refugee crisis from South Sudan, here in Guinea, they faced arguably a much more devastating crisis with the Ebola outbreak in 2014-2015. Of course, this led to active screening stopping. Medical activities were interrupted. Passive screening also was declining because people had so little faith in the health system, were very worried about going to health facilities. So during this period, there was very little going on in Boffa West, whereas in Boffa East, where they had already introduced tiny targets, they weren't able to do any of the medical work, but they did actually continue Tsetse control. So throughout the whole Ebola crisis, tiny targets were deployed, both years in Boffa East. And this is because the program there works with the community and they have a very good relationship with the community. So they use people from the community for the deployment, and this continued, as I said, during this period. And then afterwards, when the crisis was over in 2016, and they went back in and did medical surveys in Boffa West, they found that the prevalence had risen from 0.7% in 2013 to 2% in 2016, and in some villages up to 5%. And then Boffa East, they found that they had maintained this 80% reduction in the tsetse fly numbers, and they couldn't find any cases. They did look, but they couldn't find any. So that's really where we got to with introducing tsetse control at scale. And obviously one of the important things is, what are the costs? Is it effective? So economic analysis has been done by Alex Shaw using data from Uganda and Chad. And we've found that the cost of vector control using tiny targets is reduced by more than 80% compared to using traps for controlling riverine populations. So it's gone down from $440 to between $440 and $1,100 to about $77 per kilometre square with tiny targets. And this just shows the differences between Uganda and Chad. So in Uganda it's about $76, and in Chad it's $66 per kilometre square, which equates to an annual cost of between 20 cents and $1.40 per person protected. So those are the first four countries. Sadly, we can't ignore DRC, which is by far the most important country in terms of contributing the number of HAT cases. So in 2014, globally, there were 3,679 cases of Gambian HAT, and of these, 3,200 were from DRC, so over 87%. And then even within DRC, 1,885 cases were from the former Bandundu province, which is a huge area covering almost 300,000 square kilometres, so it's larger than the UK. And this one province was contributing more than half of all global GHAT cases. So while we've been working in these four countries previously, we can't not work in DRC if we want to eliminate GHAT. So DRC has a long history of screening and treatment, and they have a huge operation of screening and treating populations in the country, which they've been doing for very many years. They don't have very much infrastructure for vector control. In fact, they only have 2 entomologists working on vector control within the national program. And it's really not been a priority, and it's not something that has been done in any systematic way previously. And modelling has shown, using data from Bandundu province, that if we just continue with the strategy of screening and treatment, we're not going to get to the elimination goal. In fact, elimination won't happen until, at best, 2059, at worst, 2092. And that depends on if we were to maintain screening levels at current average levels or increase the sort of maximum potential levels. Further analysis showed that if vector control was introduced in combination with screening in persistent HAT foci, then this would help drive towards the elimination goals, and the elimination goals could be achieved in time for the 2020-2030 cutoffs declared by WHO. So we started working in DRC back in 2015 in Yasabonga Health Zone. So this is one of the health zones in Bandundu. It's one of the health zones that produces the highest number of cases. So of course it's a priority for us. And this is a project that we started to really see whether or not we could put a system in place in DRC for doing vector control. So it was very much an incremental project, starting with a relatively small area of 500 square kilometers in 2015, and then scaling up to 2,000 square kilometers by 2017. As I said, there's no infrastructure, there's no system in place for vector control in DRC. So for this initial pilot project, all of the activities were overseen by one of the entomologists from Kinshasa and the postdocs from Liverpool. So, doing the surveys for pre-intervention, doing the deployment twice per year, and then doing the follow-up surveys on a quarterly basis. LSTM were present for every single activity. And then what we found was that, similar to the other countries, we're getting this reduction in population densities, almost 90% reduction after the first deployment of tiny targets relative to what we had before the intervention started. So we do deployment twice per year and then a quarterly entomological monitoring. So there's this nice reduction, and it's been sustained over the duration of the project. So it looks like we can use tiny targets here in DRC as well as in the other countries. And then this is just a little bit of the reality of working there. So the teams deploy targets from these traditional dugout canoes. They go down the river putting out targets every 50 meters. They sleep in the field, and they sort of do relatively long distance of the river, about 60 kilometers of river they can cover in 7 to 10 days. And each of these targets is recorded in a GPS unit as well, so that we are able to monitor what's been going on as well. But Yasabonga is just one health zone in Bandundu, which, as I said, is 300,000 square kilometers and produces more than half the world's cases. And no infrastructure, no system in place for vector control, so scaling up is a challenge, of course, and needs to be done in a targeted way. We've got limited resources. We need to make sure that the resources are being put to the best use. So to decide where to scale up to, we developed a two-stage approach where we would first of all identify priority health zones for vector control, and then in the second stage identify within the health zones whether there are priority areas, rather than just doing blanket coverage of the health zone, so that the vector control becomes really, really targeted. This led to us identifying 11 priority health zones, and the map here on the left shows the case density, so it really shows the hot spots. And then the map on the right shows when vector control is going to be introduced into each of these areas. So it's 11 health zones and 14 intervention areas across the 11 health zones. And by the end of 2021, this would mean vector control over close to 12,000 square kilometers. So this is about 4% of the size of the former Bandundu province, but it does cover roughly 50% of the cases that were declared between 2011 and 2015. So it emphasizes the importance of doing this targeted approach. We're only having to cover 4% of the province to get 50% of the cases. And the areas highlighted in green are where we've been working for the longest. So Yasabonga we started in 2015, then the other green areas in 2016, yellow intervention areas started last year, the red ones will become involved in the project this year, and the orange ones will be for 2021. So by the end of 2021, we'll be covering 12,000 square kilometers. We're working really closely with the program to help them in this scale up, helping them with the planning and providing them with technical support for all of the different activities. And then also one of the really important aspects of this project is strengthening the capacity of the national program. At the moment, 2 people in Kinshasa can't do vector control over 12,000 square kilometers. So, we need to put in place a system which involves the central level, the provincial level, and the health zone level, similar to the system that's in place for medical activities. We need to make sure that there are people at those different levels who are trained on TETSI control, but who are also equipped with all the materials that they need in order to do the project. Sensitizing the local communities, of course, is a key part of it as well. There needs to be buy-in in order for the success of the project. And we work with an anthropologist at ITM, who's one of the partners on the project, on the sensitization work package for the project. And then we're also developing new systems for data collection, new systems for planning. So it's really a radical change for putting in place a vector control system in DRC over a 3-year period. And then that just gives a sort of overview of the current level of tiny target operations. We're working over 5 countries, and these 5 countries accounted for 88% of all GHAT cases that were reported between 2009 and 2018. Tiny targets cover about 14,000 square kilometers and protect a population that's estimated to be close to 2 million people currently, and then that will increase as things scale up in DRC next year as well. And then this just shows what the GHAT situation is like at the moment from 2009 to 2018. So, there have been impressive declines in the case numbers. We had about 10,000 back in 2009, and now in 2018, the number of cases reported was 953, which means in 2017 we got to less than 2,000 cases, so achieving that elimination goal that WHO set of less than 2,000 cases by 2020. And then to conclude, it seems a bit crazy that we've done all of that in such a short period of time. Back in 2011, 20 tiny targets were deployed on an island in Lake Victoria, and reduced the population by 99%. Here we are, fast forward to 2020. We're in 5 countries across 11 foci, 14,000 square kilometers a year, deploying 100,000 targets per year. And then by the end of next year, that's going to double. It's going to be 200,000 targets over 20,000 square kilometers. So to get from a research project that was in its infancy back in 2007 to this sort of large-scale control in 10 years is really quite a cool story to be part of, I think. And then, of course, also important to add that there has also been a change in strategic planning or strategy for GHAT control. WHO have included vector control now as a crucial tool for controlling and eliminating Gambian sleeping sickness. And we also have an industrial partner who is very committed to eliminating GHAT. Vestigard produced the tiny targets, and they have pledged to donate 100% of the targets for the elimination cause. So there's a lot of partners to thank. National control programs in Chad, Ivory Coast, DRC, Guinea, Uganda. Lots of partners in terms of academic partners, IRD, CIRDES, ITM, operational partners, NOMISA, PATH, Blue Square, FIND, and of course funding from the Gates Foundation, Cargill Foundation, and BBSRC, and also the TETSI group here at Liverpool, past and present, all hopefully listed there. Sorry, Sophie. Sophie Dunkley should also be on the list. So it's thanks to these people that all of this work has been possible. So, thank you.
Thanks very much. That was excellent. It's amazing story. Do you know, when you started, you said something about knocking out 4% of the population per year to achieve elimination. Have you got any idea what percentages you've achieved in the different countries?
Difficult to say in terms of percentage of the population. Obviously, we're achieving a really high percentage of control in terms of the numbers that we're getting in the traps. So 80% reduction. And the modelling has shown that even if we get a 60% reduction in our trap catches, then that would lead to elimination. So in terms of overall population, it's difficult to say, but definitely on the right lines in terms of what we are achieving.
So,
if I understood you correctly, in Uganda, having scaled up your coverage initially, it's somewhat scaled back more recently. Have you seen any resurgence in the population of tsetse in those areas and therefore increase in cases?
So there are two areas in Uganda that we have already started to scale back in two districts. And these are districts that have had control for a long time and have had a long time of having no cases. So there is an increase in the number of flies, but there's no increase in number of cases at the moment. And then actually in the current project, the new Trapano 2 project, we'll continue to scale back further and see what happens. We'll still be present, so if things do start to get worrying, then we can respond. But it will be an interesting opportunity to have a look and see in an area that's had 5 years of tsetse control, populations reduced by 90%. What then happens once you stop control? How long does it take for populations to rebound to the sort of pre-intervention level? But certainly no cases.
I had a couple of questions. Oh, there's one at the back. I still have my couple of questions.
Thank you, Andrew. Thank you, the team. That is a really fantastic presentation and really promising in research. So my question is about climate change, and I wanted to know whether there has been there's any connection that with such a changing climate, whether this beautiful story could change.
It's a good question. I wish my colleague was here to answer. I would say undoubtedly climate change will have an impact. Jen Lord has done some analysis in Tanzania, in Zimbabwe, so she would be better placed to answer. Lame answer.
Thank you, Andrew. That was a wonderful presentation. Just often we see when interventions like this are implemented on scale, that there can be sort of unexpected benefits, and something that comes to mind, of course, is with the mosquito, the bed nets for malaria prevention having a positive impact on LF and things like this. Have you seen or explored or anticipated any sort of secondary or unexpected benefits from the large-scale implementation? And equally, maybe the flip side, have there been any unexpected or unintended consequences of this large-scale act?
We haven't explored any other unexpected consequences. I suppose one of the things in many of the countries is that the focus so far has been really on building a system and making sure that this is a secure system in place for tsetse control first and foremost. We have been asked whether we can use the system that we're putting in place in DRC, for example, to introduce other vector control methods for other diseases, but at the moment we're not at that stage. So in terms of unexpected benefits, I can't think of any at the top of my head.
I'm
And
sure they're
absolutely
there.
no negatives.
Look harder, we'll find some.
Oh, there's a couple. There, I think.
Thanks for that presentation. I just wanted to ask about the thought process behind the safety of staff from LSTM and the teams that are working there in the DRC. Like, what kind of things goes into making that decision? Okay, we're going to send a team into this area of DRC.
It's a really good question. So I suppose first of all I should say that where we work in DRC is very far away from where the current Ebola outbreak is, and also very far away from where the violence and fighting in the east of the country. So in those respects, we're in a fairly safe place. Then in terms of safety in the field, everyone gets a satellite phone because there's not particularly good phone coverage, so you have an emergency phone that you would be able to call if you needed any help. Safety in terms of life vests for all of our team members, as you can see. And we do risk assessments before we travel, like anybody would for going to any country. We work with the national program. We're never in the field by ourselves. We're always there with our partner. So I think it's fairly safe. Obviously anything can happen, but I think we sort of do what we can to ensure we've got a safety and security protocol as well, where we know where all the hospitals are, embassy phone numbers and things like that. So yeah.
Question at the back.
Hello, a quick question about community acceptance. How have people been responding to the traps, and what challenges have you faced? And what's the difference been like between the countries that you've worked in? Because they're probably all quite different, aren't they?
So I would say broadly, very positive. I mean, I think Guinea is a really nice example of how the local community sort of really does accept it, and the fact that they were able to continue Tetsu control throughout the Ebola crisis. When Ebola was going on and medical teams would come to villages, the villagers wouldn't let people in. They were so suspicious of everyone coming from the outside. But when the team came from the National Programme for Tetsu Control, they were recognized, they were accepted, they were able to continue working. Uganda as well, I would say that we've got pretty good acceptance there. DRC is a bit more interesting. So as I said, we work with a social anthropologist from ITM. So she's done quite a bit of work looking at the acceptance of the work in the first area that we started working in Yasabonga. And there are sort of all sorts of rumors and things that go with the work that we're doing. Are we there to steal mermaids from the rivers? Are we there to steal diamonds and things like that? So it really highlights the importance of good community sensitization in DRC. And with the new project, with the Scale Up project, we've made a really conscious decision to make much more of an effort on that side and really sort of use the traditional communication channels which would be used for all other diseases. So yeah, learning lessons and hopefully improving things.
Question over here. I'm not sure that mic is switched on. Is it? Oh, yeah, good.
Thanks, Andrew. That was a fascinating journey. I loved your slide 50, where you showed how a simple island study could lead to such tremendous outcome across many other countries. This is a question following up from what Justin asked about positive outcomes. And you haven't touched on the incidence of animal trypanosomiasis. So particularly in the villages where that may have been a problem in the past, have you noticed any other indicators of a loss of trypanosomiasis in those other species?
So we haven't been looking at it because it's now an implementation project rather than a research project. But we have recently gone to work with Find in Uganda and started doing some cattle sampling. So they are looking actually at that now, particularly in areas close to where we have been working on areas where there hasn't been any intervention. So it's kind of ongoing at the moment.
I'm going to jump in with my question now before somebody beats me to it. The Vestergaard is making the traps. It struck me that it wouldn't be technically difficult to make it. Is there profit to be made? Does this raise a quality control issue?
So Vestergaard produced the targets, and they also produced the traps that are used for monitoring. The targets, the production is similar to LLIN production, where the insecticide is impregnated in the fabric.
Or not?
Is meant to be impregnated during the production process. So to try and switch that to local production in one of the countries would be difficult, and I think would
No, but my
have
point
quality
is,
control.
if there is profit to be made, might unscrupulous people make it the equivalent, but not bother with the insecticide.
Well, there probably isn't profit now that they're going to be donated,
Aha.
so there's no market. But then in terms of traps, so DRC, the national program there, have a long history of making their own traps.
Yes.
So they do that, and we do sometimes use their traps as well as the Vestergaard ones.
And I'm sorry I
Hi, Andrew.
took advantage.
Do you think that the tiny target could induce selective pressure on the fly population, like selecting for those flies that are not so much attracted by them, and then have a switch on the behavior of the mosquito, kind of behavioral resistance?
I don't think so. There's not really been any sign of resistance in tsetse fly previously. Their biology doesn't really lend itself to it either, I wouldn't say. So I wouldn't say so.
Thanks.
Not something that we're particularly worried about, is it? Yeah.
Time ticks away. Been a quite lively question and answer session. Any more Parthian shots before we finally close? Then we should just thank Andy and also Steve for an excellent talk. Thank you very much.
Thank you.